Welcome all to another session of data structure, that is graphs. I, Dr. Jyoti Pillai, Billa Institute of Technology, CSV2, will be giving a lecture on graphs. Graph is a data structure that consists of a set of nodes and set of edges, which are also called as links, arrows, arcs or lines. A graph is defined as follows: G equal to VE, where V is a finite non-empty set of vertices and EG is a set of edges used to connect those vertices. The vertices could be internal graph elements or external items represented by integer indices or references. The set of edges describes relationship among the vertices or nodes. A graph GVE with 5 vertices and 6 edges is shown in the figure. VG1 is equal to ABCD set of nodes. E set of edges of G1 will be equal to AB, BC, CE, ED, DB and DA. Let us now see different graph terminologies. First is multiple edges, or also called as parallel edges or multi-edge. Two or more edges that are incident to same two vertices. That is, if two vertices are joined by two or more edges, then edges are called as multiple edges. For example, multiple edges are useful in the consideration of electrical networks. Second term, self-loop or buckle is an edge in the graph that starts from one of the graph's vertices and ends on the same vertex. Edge or whose endpoints are single vertex and is drawn from vertex to itself is called a self-loop. For example, in graph G1, V is a vertex for which it has an edge V and V forming a loop. In graph 2, there are two loops formed at vertices A and B. In the third example, that is in graph G3, there is one loop formed at vertex 1. Now, adjacency, adjacent or neighbor nodes. Two nodes or vertices are adjacent if they are connected to each other through an edge. Vertices that are both endpoints of the same edge, those are called as adjacent nodes. For example, in graph G1, vertex V1 has two vertices V2 and V3. Adjacent edges are two distinct edges that share an end vertex. In graph G1, for example, edges E1 and E2 share same end vertex V1. Edge cost is the value that an edge holds to travel to another vertex. The weight of an edge or edge weight is also referred as cost of that edge. In many applications, weight may be a measure of the length of a route, the capacity of a line, the energy required to move between the locations along a route, etc. For example, edge costs of A to B and B to H edges are 15 and 5 respectively. Order of a graph is the number of vertices in the graph, and size of a graph is number of edges in the graph. So, in our example, we can see that order is equal to 8 and size is 5. Order is equal to 5 in the second graph and size is 5. A path is a sequence of vertices such that there is an edge from each vertex to its successor. A path is simple if each vertex is distinct. A circuit is a path in which the terminal vertex coincides with the initial vertex. For example, in the graph shown, simple path is from 1, 2, 4, 5. Path is 1, 2, 4, 5, 4 and circuit is 1, 2, 4, 5, 4, 1. A path from a vertex to itself is called a cycle. A graph is called cyclic if it contains a cycle, otherwise it is called acyclic. Degree of a directed graph, that is number of edges incident on a node or number of vertices connected to it, is called the degree of the graph. For example, in the figure, the degree of B is 2 since two edges are coming to the node B. In degree of a node is number of edges directing inwards on a node. Out degree is defined as number of edges directing outward from a node, and degree is in degree plus out degree. For example, in the graph, the in degree of the node 2 is 2 and out degree, that is number of edges outgoing from the node 2, is 3. Now let us see about the graph representation. That is the technique which is used to store graph into the computer's memory. There are two ways to store graph into the computer's memory: sequential representation and linked representation. Graph representation can also be done in the three ways: set representation, sequential representation and linked representation. Set representation of a graph involves two sets. One is set of vertices, for example v equal to v1, v2, v3, v4, and set of edges e equal to v1, v2, v2, v3, v3, v4, v4 and v1. This representation is efficient for memory but does not allow parallel edges. Sequential representation of a graph can be represented by means of matrices, adjacency matrix, incident matrix and path matrix. Adjacency matrix includes information about adjacent nodes. Here Aij equal to 1 if there is an edge from Vi to Vj, otherwise 0. It is a matrix of order V cross V. For the given undirected graph, an adjacency matrix can be seen like this. That is, there is no directed path between or directed edges between the nodes. So it is an undirected graph and the corresponding matrix can be seen in the figure. With 5 nodes, there will be 5 rows and 5 columns, V cross V matrix. For the given directed graph, the adjacency matrix will be seen using the path or the edge directed towards another node. So the value which will be stored at Aij for the node A will be AA will be 0, AB will be 1, AC will be 1, since there is an outgoing edge from A to B and A to C. But there is no edge from B to A, that's why B of A will be 0 in the matrix. For the given undirected weighted graph, where every edge is given a particular weight value, an adjacency matrix will be consisting of the weights if there is an edge between the nodes. For example, the edge from A to B has the weight or value 7, so 7 will be stored in the position of the corresponding matrix. The second matrix, that is the incidence matrix, includes information about incidence of edges on the nodes. Here Aij equal to 1 if jth edge Ej is incident on ith vertex Vi, otherwise it will be 0. It is a matrix of order V cross E. In incidence matrix of directed graph, 0 is used to represent row edge not connected to column vertex. 1 is used to represent row outgoing edge to column vertex. -1 is used to represent row incoming edge to column vertex. Incidence matrix of the given directed graph representation can be seen from this figure. E1 is the edge from A to B. It is a outgoing edge from A. So from A to B there is an edge. So E1, E2, E3, E4, E5, E6, E7, E8 are the edges which will be forming the columns. Okay. So there is an edge from A to B originating from A, that's why the first element of the matrix will be 1. The third matrix, that is the path matrix, includes information about simple paths between two vertices. Here Pij will be equal to 1 if there is a path from Vi to Vj, otherwise 0. It is also called as a reachability matrix of graph G. Next representation of the graph can be done through linked list. This representation gives information about the nodes to which a specified node is connected, that is through adjacency lists. This representation gives the adjacency list of vertices with the help of array and linked list. In the adjacency list, the vertices which are connected with a specific vertex are arranged in the form of lists which is connected to that vertex. For example, in this undirected graph, the adjacency list of each node A is connected to B, B is connected to D, and D can be said as the last node of the first adjacency linked list. Now, if we take B, B is connected to A is connected to D, and D is connected to C. So, it is the linked list for the second node. Likewise, adjacency list can be represented by the linked lists for each node. In the directed graph, we will be seeing the direction of the edges, and accordingly the adjacency list for each of the nodes will be created. For example, for the first node 0 is connected to 1, 1 is connected to 2, and 2 can be connected to 3. Okay, so this is the adjacency list of the node 0. Next, it can be represented by edge lists. Edge list is a simple list but poor way to represent a graph. Assuming the graph has no nodes that are disconnected, that is, no edges incident to a particular node, list all the edges as pairs of vertices. For example, G equal to VE is having the set of nodes V1, V2, V3, V4, V5, V6, that the edge lists are V1, V2, V1, V3, V2, V3, V3, V4, V4, V1, V4, V5, V4, V6 and V5, V4. Now, let us discuss about some of the types of graphs. Depending upon the position of the nodes and the vertices, there may be different types of the graphs. The first is null graph. A graph G equal to E where E equal to 0 is said as null graph or order 0 graph or empty graph. That is, a graph with an empty edge set having no edges connecting any pair of vertices. The null graph consists of only isolated vertices in the graph with vacant edge set and no connections between the vertices. For example, the images displayed are null or 0 graphs as it has no edges or 0 edges between the 3 vertices of the first graph. Second is trivial graph. A graph G equal to VE is trivial or singleton or single vertex graph if it contains only a single vertex and no edges. It is the simplest possible graph that can be created with least number of vertices, that is only one vertex. It can be used as a starting point for building more complex graphs. For example, the figures are examples of trivial graph having only a single vertex in the whole graph named vertices A. Next is non-directed graph. A graph G equal to VE is called a non-directed graph if all edges present between any two nodes are non-directed, that is, edges don't have any direction. Undirected edge has no orientation, that is, no arrowhead. It is hard to identify the starting and ending node by looking at the edges in the non-directed graph. The graph shown is an example of a non-directed graph. There are 4 vertices A, B, C and D and 4 edges between the vertices which are not directed. That is, edges don't have any specific direction. The edge between vertices A and B does not have any direction, so it cannot be determined whether the edge between the vertices A and B starts from vertex A or vertex B. Similarly, we cannot determine the ending vertex of the edge between A and B. Directed graph. A graph G equal to VE which has every edge mapping onto some ordered pair of vertices Vi, Vj is called a directed graph or digraph. All edges of a digraph are directed or have a defined direction. By directed edges, it is easy to determine from which node it is starting and at which node it is ending. Directed edge has an orientation, has an arrow head. The graph is an example of a directed graph. Here in the figure, E1 is an edge which is directed from V1 to V2. E2 is an edge which is starting from V2 and ending at V3. E4 is another edge which is starting from V2 and ending at V4. Connected graph. A graph G equal to VE is said to be connected if any pair of vertices Vi, Vj of a graph is reachable from one another. That is, if we start from a node, we should be able to visit every other node of the graph. In a connected graph, there must be at least a single path between every pair of vertices. Starting from vertex B and traversing to H, there are various points in the or paths in the example connected graph. One of the path is vertex B to C to D to F to E and then ending at H. Similarly, there are other paths for traversing the graph from vertex B to vertex H. Disconnected graph. A graph G equal to VE is said to be disconnected if any pair of vertices do not have a path between them. In a disconnected graph, starting from any node of the vertices and moving to the remaining vertices, there exists at least one pair of vertices that does not have a path between them. For example, if you want to traverse from vertex A to vertex G in the figure shown, then a single path does not exist between the two vertices A and G. So, this is a disconnected graph. Labeled graph. A graph G equal to VE is called a labeled graph or weighted graph if vertices and edges of the graph are labeled with value, name, date or weight representing the cost of traversing that edge. For example, in the unweighted graph, the edge will be a directed edge and will be having some value, and node also will be having some value. So, unlabeled graph will not be containing any value in the edge and the node part. Edge labeled graph will be containing value in the respective edges or in all the edges. Vertex labeled graph will be having values at the nodes of the graph. Regular graph. If all graph nodes have same degree, then graph is called as a regular graph. If all vertices in the graph are of degree k, then it is called as a k-regular graph. That is, if all vertices of a graph are of degree 6, then it can be called as a 6-regular graph. For example, in graph G1, there are 3 vertices named as vertex A, B and D. 2 edges are associated with A, one from B and another from D. So, degree of vertex A is 2. Similarly, degree of B and D is 2. That is, G1 is called a 2-regular graph as degree of all the 3 nodes of G1 is having value 2. In G2, there are 4 vertices named E, F, G and H. Degree of all 4 vertices of G2 is 2 as only 2 edges are associated with all vertices of G2. G2 is also a regular graph as all nodes have same degree 2. Complete graph or full graph. A simple graph G equal to VE with n vertices is called a complete graph if degree of each vertex is n minus 1. That is, one vertex is connected with n minus 1 edges. A complete graph of n vertices is represented as Kn. In a complete graph, exactly one edge is present between every pair of vertices. That is, each vertex is connected to every other vertex. For example, a tournament graph where every player plays against every other player of the team. Graph K4 has 4 nodes E, F, G and H. F has 3 edges connected to other 3 remaining vertices of K4. Likewise, other 3 remaining vertices have 3 edges associated with each one of them. All vertices of the graph K4 has a separate edge for other vertices. Hence, it is a complete graph. Next is cycle graph. A graph G equal to VE consisting of n vertices where n is greater than or equal to 3 and edges form a cycle. Then the graph is called a cycle graph. In a cycle graph, the degree of all the vertices will be 2 and there will be at least one cycle. For example, a bike sharing graph where cycles represent the routes that the bikes take. In the graphs shown G1, G2, G3, all are cyclic graphs as number of nodes for all graphs is greater than or equal to 3 and degree of all vertices of the graph is exactly 2. A graph G equal to VE is called as a cyclic graph if it contains at least one cycle, or we can say it has a minimum of one cycle present in the graph. The graph G1, for example, has 2 cycles present in it, satisfying the required condition for the graph to be cyclic, thus making it a cyclic graph. Similarly, the graph G2 contains only one cycle, hence G2 is a cyclic graph. The next is acyclic graph, which is opposite of the cyclic graph. This graph will be having no or 0 cycles present in it. An acyclic graph is the complete opposite of the cyclic graph, like I said before. The graph shown is acyclic because it has 0 cycles present in it. That is, if we begin traversing the graph from vertex B, then a single path will not be existing that will traverse all the vertices and will be ending at the same vertex B. Next is simple graph. A simple graph is a graph that does not contain more than one edge between the pair of vertices. A graph is said to be simple graph if the graph does not consist of any self loops and no parallel edges are present in the graph. For example, a simple railway track connecting different cities is an example of a simple graph. In the figure, we have got 3 vertices and 3 edges for the graph. There are no self loops, no parallel edges, so this graph is called as a simple graph. A multigraph G equal to V can be called as a multigraph if that graph does not contain any self loops but parallel edges are present. That is, if there is more than one edge present between 2 vertices, then that pair of vertices is called as having parallel edges. For example, a road map. If a pair of nodes is connected with multiple edges in the graph, that graph is called as the multigraph and the road map can be said as an example of the multigraph. In the example figure, we have 3 vertices and 3 edges for the graph. There are no self loops but 2 edges are connected between the vertices A and vertex E of the graph. Planar graph. A planar graph is a graph that cannot be drawn in a plane such that no 2 edges of it cross each other. The graph shown is a planar graph as it cannot be drawn in a single plane with no edges intersecting. Next is Hamiltonian graph. A Hamiltonian path starts and ends at the same vertex and that is called as Hamiltonian circuit. Suppose a closed walk in the connected graph that visits every vertex of the graph exactly once without repeating the edges. Such a graph is called a Hamiltonian graph and the walk is called a Hamiltonian path. The graph consists of a closed path A, B, C, D, E, F and back to A, which starts from vertex A and traverses all other nodes without traversing any of the nodes twice other than vertex A in the path of the traversal. Therefore, this particular graph is called a Hamiltonian graph or Hamilton graph. Next, finite graph. The graph G equal to VE is called a finite graph if it has a finite number of vertices and a finite number of edges. That is, number of vertices and edges in the graph is limited in number. A finite graph is represented by an adjacency list, which is a collection of unordered lists. Each unordered list describes the set of neighbors of a particular vertex in the graph within an adjacency list. The graph shown in the image is a finite graph. There are 4 vertices named A, B, C and D, and the number of edges present in the graph is also 4, limited in number. So, we can say that as both the number of nodes and vertices of the graph is finite in number, the graph is a finite graph. Infinite graph. A graph G equal to VE is said to be infinite if it is having infinite number of vertices as well as infinite number of edges. For example, in the graph, number of vertices in the graph and number of edges in the graph are infinite. So, this graph is called an infinite graph. So, we have seen today that what is a graph, what are the nodes and vertices of the graph, what are the different terminologies which can be used in the graph explanation, then how the graph can be represented in the memory, the different ways of representation of the graph, set representation, graphical representation, sequential representation. So, we have seen the different representations of the graph, the different types of the graphs also, with some examples of the different types of the graphs. Hope the lecture is cleared the doubts about all the types of the graphs and the different representations of the graph. Thank you very much.